Hello, my name is Doron, and I'll talk about approximating iterated multiplication of stochastic matrices in small space. This is joint work with Cohen, Sberlo, and Amnon Ta-Shma from Tel Aviv University. And at STOC, this is joint talk with Louis and Ted's paper, Near Optimal Derandomization of Medium Width Branching Programs. So what's our problem? We're given W by W real matrices A1 up to AN, and we wish to compute or approximate their product. It's obviously a very natural and fundamental algorithmic primitive. And also, for numerous reasons, it's an important problem in complexity. For us in the space-bounded world, we can get better understanding of space-bounded computation models through the lens of canonical linear algebraic problems. Specifically, today we'll discuss the space complexity of the IMM problem. And I'll motivate this problem very soon. But first, let's discuss the model of space-bounded computation. Let's start with the probabilistic model. We have an input tape, which is read-only, so note that we cannot replace the input with intermediate computations. We have a random coins tape, which is initialized with uniform and independent random bits, and it's read-only and unidirectional. We have our work tape, which is read and write, and it's the only place in which we can store intermediate computations. And we have our output tape, which is write-only and unidirectional. And the space complexity is just the number of cells used on the work tape or tapes. And note that if we want to store, for example, previous coin tosses, we cannot do that on the random coins tape because it's unidirectional, and we need to store them in the work tape. And if we're interested in deciding languages, we say that the language is in BP space f of n if it's accepted by a probabilistic space-bounded machine with space complexity O of f of n, and we allow bounded two-sided error, let's say of a third. And similarly, of course, we can talk about approximating the function rather than accepting or rejecting. For example, the IMM problem, where we want to use few bits of auxiliary memory to compute or approximate A1 up to AN with high probability. And our goal in de-randomization is to get rid of those random coins, and the deterministic space-bounded model is just the same, but we dispense with the random coins, and the corresponding complexity class is D space. And again, we can talk about approximating a function deterministically space efficiently. And indeed, this is what we'll do today. So what's our goal? Our goal is to take any space S randomized algorithm and turn it into a space S prime deterministic one, hopefully without paying much overhead. So hopefully with S prime, which is O of S. And this is what's called the BPL versus L problem. And indeed, BPL equals L if you believe circuit lower bounds. But unlike the time-bounded model, we do have explicit results and, in fact, significant progress over the past decades. So what do we know? First, we can extend Savage's result and show that BPL lies in L squared, which is D space log squared n. Nissan gave a de-randomization of BPL, which works in space log squared n and simultaneously takes poly time, and this uses Nissan's generator, which we will talk about very soon. Sex and Joe cleverly built upon Nissan's generator and showed that BPL lies in L to the 1/2. And very recently, we have an improvement, a lower order improvement on Saxon Joe that utilizes recent machineries in the recent machinery in weighted PRGs. And we also have other milestones, which I won't talk about today, and also nearly optimal results, not for BPL, but for more restricted classes of computation. For example, for those of you who know, PRGs for various classes of branching programs. Okay, so let's start with computing IMM exactly. What do we know? You can do repeated squaring, and do it in space O of log n times log n w. Recall that w is the dimension of the matrices and n is the number of the matrices, the number of matrices we wish to multiply. So when n and w are polynomially related, this belongs to the class L squared. Okay, but what about approximating a1 up to an? Now, the game is between L and L squared. Well, actually, you can be a bit more refined, but we won't get into it today. And for general operators, nothing better than L squared is known, even for approximating the product. But can we do better if we restrict A? And generally speaking, doing approximate linear algebra on several restrictions of A captures important complexity classes. So looking at symmetric operators, this is captured by BQL, which is the quantum analog of BPL. Restricting A to stochastic operators, this is captured by BPL, and indeed this is what we will talk about today. Restricting A to doubly stochastic operators, this is actually already in L tilde, nearly L, and this is a recent line of exciting research. But again, our focus today is on BPL and arbitrary stochastic matrices. Now, approximating A to the n for n and w being polynomially related is actually complete for BPL in the sense that we can convert any probabilistic space-bounded Turing machine into a stochastic matrix A such that the probability to move from S to T is just A to the n in the location ST, and vice versa. We can approximate any entry in A to the n by taking random walks. So de-randomizing BPL in space O of S corresponds to approximate matrix powering deterministically in space O of S. And what do we know when we want to distinguish n and w? So we can do iterated powering and truncation and get roughly log n times log w. We can use Nissan's generator or the INW generator by Impagliazzo, Nissan, and Wigderson to do it even in a black box manner in space of log n times log n w. Saxon Joe's result gave us log n to the 1/2 plus square root n times log w. And you might wonder, well, what's the corresponding de-randomization problem when we want to distinguish n and w? And they're not necessarily polynomially related. So it's not hard to show that de-randomizing two-sided error algorithms that use log w space and n bits of randomness is roughly equivalent to approximating A to the n deterministically, where A is of dimension w. And what's our result? We approximate IMM, where each AI is stochastic, to within high accuracy using only O tilde log n plus square root log n log W space. And in the medium W regime, where say W is 2 to the square root log n, we get the nearly optimal O tilde of log n space. So what do we use for our result? We use two classical results. The first of which is Nissan's generator, and we actually view it not as a PRG in this talk today, but as a randomized matrix powering algorithm, and I'll talk about it very soon. And we also utilize Saxon-Joe's approach, which again cleverly uses Nissan's generator together with the shift and truncate technique in order to recycle randomness, and I'll talk about it today too. And beyond these two classical ingredients, we use one which is a bit more recent, not in general, but in the space-bounded literature, which is the preconditioned Richardson iteration, which is a very basic primitive in the time-bounded works as an iterative method for solving linear systems. And it's recently appeared in quite a few space-bounded works as a way to obtain high precision approximation of matrix powers and inverses from mild approximations of powers or inverses. Okay, so most of today's talk will be on the case when A1 up to AN are the same matrix, because even here we have quite a few challenges. Okay, so let's talk about Nissan's generator, which can be viewed, as I told you, as a randomized matrix powering algorithm, which is a very space efficient, and I'll show you the parameters in a minute, but it needs a relatively large number of random bits, and these are offline random bits. We cannot just toss them and forget them, but we need repeated access to those random bits. In terms of parameters, this is Nissan's generator as we view it in this talk today. We're given a matrix, a W by W matrix, where each entry is represented by S bits. We're given some accuracy parameter epsilon, some confidence parameter delta, and the algorithm on a random seed H approximate A to the N such that with probability at least 1 minus delta over the H's, it uses space which is logarithmic, log NW over epsilon delta, but the length of H, the number of bits needed to represent H, is roughly log squared n. So it's S plus log NW over epsilon delta times log n, okay, which is too much for us. But we use it as a component. And what's the original Saxon-Joe algorithm? They take Nissan's generator as an approximated matrix powering algorithm and do it iteratively. So they apply Nissan to the power of 2 to the square root log n for square root log n times. Okay, so if you think about it for a minute, if you do it, you'd get A to the n. Okay, but the obvious question is, with which h's? So one option is to take independent h's at each iteration, and that would be too costly. Another option is to take the same h across all iterations. But why would it work? There is an adaptivity issue. Even if one layer of the recursion succeeds, and for example, Nissan AHR is a good approximation for many h's, The output of Nissan's algorithm depends on H, so future iterations might fail miserably. But a good AH, a good output of Nissan's algorithm, should not heavily depend on H, right? Because it approximates some quantity that does not depend on H. So how can we get rid of the dependence? And this is what Sachs and Joe solved in a beautiful manner. So what they did is they used random shifts. So say we choose a random shift zeta, and then we shift each entry of the output matrix, which recall that depended on H. Now we can show that with high probability over zeta, our shifted value is good in what sense? In the sense that if we truncate the result, and I won't get into the parameters, then for most inner randomness, in our case for most h's, we get a value that does not depend on h itself. It may depend on the shift, but the shift does not depend on the inner randomness of Nissan's algorithm. And once we truncate, we're guaranteed to be close to the actual power, which recall is independent of the random seed that we use for Nissan's algorithm. And this enables Sachs and Joe to eliminate dependencies between consecutive applications of Nissan's algorithm. Now I know it's been a bit rushed, but you're encouraged to look at our paper, and we give a fairly thorough overview of the Sachs and Joe approach. Okay, so what's Sachs and Joe's algorithm? They draw a single H at random and square root log n independent random shifts. And for square root log n iterations, they apply Nissan's generator. I'll just say that each zeta takes roughly log n bits. So they apply Nissan's generator for square root log n times, each time to the power of 2 to the square root log n, to some accuracy, say 1 over n squared, and then they shift and truncate each entry to some accuracy, say 1 over n. Okay, and of course this is a randomized algorithm, so to de-randomize it, they average over all h and zetas. And if you look at what's the space complexity of the algorithm, we have this factor, which is the number of bits required to store all the zetas. And we have this factor, which is both the length of h and also the space complexity needed for Nissan's generator at each iteration. So we have log r iterations. Each iteration takes log rw over epsilon space. Overall, this gives us log to the 3/2 n. So what are our bottlenecks? The first bottleneck is that the magnitude of each shift is 1 over poly n, and we use square root log n of them. So overall, this incurs an overall factor of log to the 3/2 n. But our observation is that we can actually use log w bits per random shift. So overall, this will require seed length of square root log n times log w, which is good for us. And let's not spend too much time on this issue, because the second bottleneck is the more challenging one to overcome, and it's that Nissan's generator is costly if the input matrix is represented using many bits of precision, or also if we require high accuracy. So if we require 1 over poly n accuracy, it makes sense that each iteration seemingly makes sense that it requires log n space, which is too much for us. But we do need to maintain accuracy of 1 over n, because the quality of the approximation deteriorates as we take higher powers. So our strategy would be, before applying Nissan, we purposely decrease the precision of the input matrix by truncating its entries to a precision of 1 over W. If we both truncate the matrices to a precision of 1 over W and use Nissan's generator with error, which is 1 over W, recall that W is much smaller than n, then the required seed length of Nissan's generator will be log n plus square root log n times log W, which is good for us. But mild approximation at each iteration is not enough. We really need the high precision approximation of 1 over n. So what do? We use Richardson iteration. So the way we use it is in the following form. Suppose we have W by W matrices A and A1 up to AR, such that each AI is some 1 over R approximation of A to the I. So it's only a very mild approximation. Then we have an algorithm that takes A1 up to AK and approximates A to the R to within very high accuracy to the minus K and uses very small space, so roughly log K times log RW. This is highly space efficient. In our case, this space complexity is log W plus square root log n. And note that we can kickstart the process once we have only a mild approximation of 1 over R. And note that we need access to the original A and also to mild approximation of all its intermediate powers. So what's the algorithm? After each mild Nissan invocation, with accuracy 1 over W, we retrieve high precision using Richardson iteration. And although we decrease the precision before using Nissan, this precision is not lost since we can still have access to the untruncated matrix. So the Richardson iteration combines untruncated matrix, the untruncated matrix, plus mild approximation of its powers that we got from Nissan in order to get a high precision approximation of the rth power. So here is a very brief outline of our algorithm for matrix powering. We start with our original matrix A. We truncate it to log W bits. We use Nissan with mild accuracy. And then we use Richardson on the original matrix and the mild approximation of all the powers, essentially, to get R0, which has good accuracy. We shift and truncate and repeat the process. Okay, so we have an alternating nature between 1 over W accuracy and 1 over N accuracy. We do it for square root log n times, and we're able to maintain 1 over n accuracy without using log n space per iteration. Okay. And with high probability over the randomness, we get a high precision approximation of A to the n. And note that everything is done space efficiently, so we never really store entire matrices, but need to do it more carefully. Okay, what about distinct A1 up to AN? So we do use a tree structure and applying Nissan iteratively to approximate IMM, but there are several challenges in doing so. And the most problematic challenge is that the shifts are now too expensive. I won't get into it in this talk, but our idea on how to solve it is that instead of shifting intermediate matrices, we shift the input matrices and use the same shift for all the input matrices. A concurrent work by Patterman and Pine had the following beautiful observation. They observed that most applications of Nissan's algorithm will be good even without the shifts. So to overcome the challenge that multiple shifts are too expensive, we handle it by doing one initial shift plus error reduction, and the Patterman-Pine paper makes no shifts and does error reduction. So I encourage you to check the video of near-optimal de-randomization of medium with branching programs by Patterman and Pine to learn more about the IMM case. Thanks for listening.